Welcome to Brain Vision.
Now we have a mass that was initially pressed onto a spring. Right, it is being compressed by a distance, so its natural length maybe around here, and it was compressed by a distance x, and then it's released, in which the apparatus now flies up and reaches a maximum height of h when compared to when it was initially compressed. So this is h. What we want to find is the force constant for the spring in terms of all these different values. So using energy conservation, we know that the elastic potential energy, half kx squared, inside the spring, stored in the spring, must be equals to the total energy that was imparted to our object, in which is converted entirely to gravitational potential energy, mgh. Now we have a second condition in which the maximum acceleration of the apparatus is a. So at this point over here, the force acting on the block is the spring, right? The spring has a force kx, and the block itself has a mass, right? This weight is mg. So net force is equals to kx minus mg, which is also equals to ma, where a is the maximum acceleration without damaging our component or our spring. So this is our second equation, which we can rearrange to actually get this equation, bringing the mg over to the right, then dividing by k, get mg plus a over k. So this can square this and substitute this into our expression, our first expression, and we get half k times now all we have left is to just rearrange this equation a bit. So we get 1 over k squared over here times k, so we will get 1 over k. We bring this k value over to the right, and we bring the mgh to the left, so we get k is equals to half times mg plus a squared divided by mgh. Simplify this a bit, we should get mg plus a squared divided by 2gh. So this is our final expression for the spring constant. For the next part, we want to find what is the distance x for the spring to be compressed. Now we know that x over here from this expression, x is equals to mg plus a over k. And so we just substitute the expression for k into this. So this is our expression for the extension.